Good afternoon, everyone. So we'll start today's session. Um, so today we are going to see this new this architecture called YOLO V5. So we'll discuss about the architecture, this deep learning architecture, and im- implement a application using YOLO V5 and IoT, and we'll integrate a IoT application with the YOLO, the application that we create using YOLO V5 architecture. So YOLO V5 is one of the CNN-based architecture, deep learning architectures that is widely used in different areas. So it is, we can use it for live video, object recognition, or object recognition. So here we are going to use it in object recognition for object recognition. So yesterday we saw this architecture called MobileNet SSD, MobileNet SSD, MobileNet single shot detector. So that is a lightweight architecture which can be used in small devices. But YOLO Wi-Fi is much more advanced than that. It will be, it's not possible to run. It will give much more latency, much higher latency values if you try to run YOLO V5 in a in a smaller system, like in a system with a less efficient processor. So it is better to use this type of systems, this type of better to run this type of architectures in a system with the proficient GPU and CPU. So we'll just first we'll see discuss about the YOLOVify architecture itself, and then we'll see the application, and we'll see how to integrate that with the IoT. So so why we should use YOLO V5, and what is the difference between YOLO V5 and existing CNN based algorithms? So YOLO V5 means it is the fifth version of the YOLO family architectures. It is an advanced architecture of the previous YOLO V3 and YOLO architectures. So YOLO divides an image into a grid system, and each grid it detects objects within itself. They can be used for real-time object detection based on data streams. They require few computational resources. So this is the advantage of using YOLO algorithm. YOLO algorithm in general. YOLO algorithm in general, it divides the input image into grids. So if we take any, so yesterday we saw the mobile net architecture where the input image is a 224 by 224 three channel image, and that image again that goes to the depth-wise convolution, and that as a result of the depth-wise convolution produces a depth map, feature map, depth-based feature map. The same in case of YOLO V5, instead of giving that taking that single image, the whole frame 24 by 24 frame as a input, it will divide that into different grids, and then each grid will be it will try to detect the object within each grid. Then they also so they can be used for real-time object detection based on data streams. A live video stream, using a live video stream, we can detect objects in a live video stream. They require very few computational resources. The computational resources are very few. Then object detection, general object detector will have a backbone. So this is just a description of object detector or object detection, process of object detection. General object detector will have a backbone of pre-training it and it a head to predict the classes and bounding boxes. Backbone can be running on a GPU or a CPU platform. The head can be either one stage, example YOLO, SSD, Retina Net. All these things do the detection in one stage. That's why they are all single shot detectors. In a single shot, they detect for dense prediction or two stage for faster RCNN. Then for sparse prediction of prediction object detector. Recent object detectors have some layers to collect feature marks, and it is between the backbone and the head. So there is another layer. So basically, in general, in an object detector, there are two parts: a head and a backbone and a head. So backbone can be running so the will backbone for pre-training it and head is to predict. So pre-training and head is to predict the outcome. So then in case of like object detectors like YOLO V5, there is another part called neck. It is between backbone and the head. So this is just a comparison between different versions of YOLO. So YOLO V3, V4, V5, neural network type FCNN, all are FCNN, and backbone is darknet 53, CSP darknet 53. It's a advanced version of darknet 53, and next is FTN, feature pyramid network. And in case of YOLO V3, and in case of YOLO V4, it is spatial pyramid pooling and path aggregation network. In case of YOLO V5, it's a SpanNet, path aggregation network, the SpanNet. And head is, in this case, it's a D into 5 output layer, number of bounding boxes, and it will generate this many output layers with B being the number of bounding boxes and C being the class node. Same as YOLO V3, same as YOLO V3. So the head is the same. The output part will be the output layer is the same. Loss function, binary cross entropy, and here the binary cross entropy and logit loss function. So we know what is the loss function and all that. You may have studied that in earlier classes. So the loss function that here in both YOLO V3 and V4, it's only binary cross entropy. Here it uses two methods uh, for loss calculation, that is binary cross entropy and logit loss function. And features of YOLO V5. So YOLO V5 follows a single shot detector. So it's an SFP architecture. It uses single shot detector approach, which means it performs object detection and classification in a single forward pass through the neural network. This makes it very efficient for real-time applications. So single site SFP type SSP detectors are object detectors are very useful when it comes to real-time applications, because you need a faster output with the less with the lower latency. Because at the same time, like we need to process maybe in real time, so that means like 32 or 40 frames per second. So that many, if the architecture should be able to handle that many frames per second. So in that case, single shot detector is favorable, is more is recommended. So in our case, all we five is a single shot detector. So in our application, it's going to be a real time video application. So we need a single shot detector in that. So, like earlier versions of YOLO V5 uses anchor box clustering to predict the bounding box dimension. So, anchor box clustering means are predefined. They are very size and aspect ratio. So, these anchor boxes are created based on the data set that is created. So, the data set is so we can. I'll show you the data set creation and all that annotation and how we can create a data set. I'll show you all that. Um, so when we create a data set, we have to do this process of annotation. Annotation means we have to draw a bounding box around the object that we want to detect. In our frame, we have multiple objects. Like in uh, in in our case, we are going to detect different type of vehicles. So cars, trucks, buses. So in a single frame, there could be cars, buses, and trucks. So we need to draw that this is a bus, this is a car. So we need to draw a bounding box around the object, specific object. So in a single frame, there could be multiple bounding boxes. So this process of drawing the bounding box is called annotation. So through annotation, we are telling the architecture that this is the object that we need. So look for this specific pattern. So by drawing, we separate the specific object, and then we feed that to the training program. And after training, it will create a number of parameter values. So these parameter values will be saved in the model file. So model file will be, these parameters are called weightages, and it will be saved in model file. So then whatever bounding box we have drawn, that the annotate during the annotation time, that dimensions will be taken as a kind of a benchmark, as a reference. So that's called anchor box clustering. So that means like we have manually annotated the images, so that will be so we are just telling the through anchor box clustering, we are just telling the model that these are the specific, like if it is a car, the bounding box dimension will be this much, the height and width will be this, and it could be this, it could be height and width could be this, and if it is a bus, the height and width could be this. So based on that, we are just based on that, it will create a reference. If it is a particular object, then the bounding box is supposed to have that particular dimension. Then it will compare that with the real-time output and the previously saved dimensions. So that's called anchor box clustering. So it is very useful when it comes to getting accurate predictions. Anchor boxes are predefined boxes with various sizes and aspect ratio. Uh, So the network learns to adjust these to fit the object in an image. So the network learns to adjust these boxes to fit the objects in the image. YOLO Wi-Fi utilizes CSP darknet as backbone architecture. This is a modified version of darknet 53 architecture, which is known for its efficiency and effectiveness in feature extraction. So YOLO V5 itself is not a single architecture, it is a combination of two architectures. We've seen that backbone is a PANnet, backbone architecture is called CSP darknet 53 architecture, and then the head is called PANnet. So it's a combination of two different type of architectures. YOLO V5 employs a feature pyramid network to extract the features at at multiple scales. This helps in detecting objects of different sizes in images. The detection head of YOLO V5 is responsible for predicting the class force, objects, corners, bounding box coordinates. It uses a series of convolutional layers to process the feature map produced by the backbone network. You already have output bounding boxes with associated class probabilities. Each bounding box is represented by four coordinates: x, y, width, height, and a conference score indicating likelihood of an object being present. Additionally, there are class probability for each detected object. So here this is just what type of format was for what type of output, the output format associated with the class probability. So each bounding box is represented by four coordinates, x and y. So it could be denoting the center of the bounding box, and then the width and height. So the program can draw a bounding box around the object, and a confidence score indicating the likelihood of an object being present. Then a confidence score, it could be the confidence score could be from 0 to 1. So 1 being 100% confident, 0 being 0% confident. Then additionally, there are class probabilities for each detected object category. Then there is a class probability other than the object confidence score. So the specific project that we are going to create here is called traffic violation detection system. So we are not going to detect any traffic violations. So showing an example of that, uh, example video of that, a small system. So creating a data set. So this is the first step that we have to go through. Like whenever we are creating a deep learning application, the first step that we have to go through is collecting data set. So we have so in our specific case, we need to detect vehicles. So vehicles means it could be car, bus, or a truck. So in a real case, like if you are trying to implement this in a real world as a project for government, like for traffic police or something like that, then you have to add all the different kind of vehicles, possible vehicles. You should not just add one, two, or three classes. You should include all the different possible vehicles, like a minivan, whether it is a car or a minivan or a truck or a bus, or it could be a bike, motorcycle, or it could be an auto rickshaw, or any kind of motorized or electric vehicle, EV vehicle should be included in that class. Then we should have a data set of like each class should have like 5,000 to 10,000 or 20,000 images, and all these should be so not each class in general, like each class could have that many images, and then in general there could be like there should be like 50,000 or 50,000 plus images, and all these images would be perfectly annotated. So this we can use so in a product based in a product based project, we have to like go through this whole, like it will take months and months to create data sets itself, because manually we have to annotate every image. I'll show you the annotation part. So I'm going to use this tool called RoboFlow. So this is a free tool, that free online tool which you can use to create your data sets. But if you take other companies like multinational companies, like different type of companies like Tesla, or companies like Intel or HCL. These companies, they have their own research going on in different self-driving and things like that. So they have their own proprietary softwares for annotation. They have their own team for doing for doing annotation. So in our case, I'm just a single person. If you're just, for example, if you're just a single person working on your own project, then in that case, you can use a tool like RoboFlow, which is affordable. So you can just so we can just go to Google and you can just search Firebase. So Firebase, and you can create a Firebase account. So in my case, I have already created an account. You can create your own account, and you can just say get started. Sorry, not Firebase. Sorry, RoboFlow. Firebase will go. So we'll be using Firebase in our IoT application. So right now we'll just go to RoboFlow, and we'll see how to create a data set. So I have created so many different projects here, and self-driving leak disease detection, so smart currency. All these are different projects that I've created. So if I take one of the examples, self-driving, I can show you the images. So it contains 5,000 images, 5,400 images, and this is a data set that we can use for self-driving vehicles to create a implement self-driving vehicles. So it has so it can in so the if you have a data set like this, you can see different type of vehicles are annotated in this here. So you can see the cars, and every car is annotated using this square. That means so this is done manually. So whenever there is a vehicle, draw a bounding box over that vehicle. So like for example, I can just say annotate. Like I can just draw the bounding box and create a specific class. So I'll show you where. So if you want to create a new project, you can't do that in this case because in this account, you can't create a new project. So we'll just use another account. So I was just drawing the example of a data set, actual data, real data set. So it contains 5,000 images, and this 5,000 images are so one when you download the image, when you download this data set from RoboFlow, that you'll get a data, you'll get the folders like this: tester, trainer, valid. So test is the so train is the first thing. The so train that folder will contain most of the images. So most of the images will be in train, and inside the train folder itself, there will be two folders: images and labels. So labels is just text files. So for example, if you take the first image here, the name is 0CC 0C for 04A1. So this is the image. So this is just a this is a gun detection. So this is to create this using this model we can create a gun detection. Using this data set we can create a gun detection model. A model that can detect rifles and pistols and revolvers and things like that. So here in this picture, this is the object of interest. We need to detect this specific object here. So what annotation, what labels will say is you can see the same name here. The text file has the same name. So when you open that, you'll see a number. You'll see numbers. So first of all, there is a number that says 0. 0 means the class index. So this is the class index. So I don't have multiple classes here. I only have one class. It's called gun. So there is no, I'm not differentiating between rifles or pistols. There is no classes. So there is no different classes. There is only single class. So every label will have the same number, first number 0. So it doesn't matter which one you open. Every label will have the first number will be the same. Then these other numbers are the xy coordinates of the object, annotated object. So in the image, so in the so that numbers tells the model, the system, the architecture that where the object is in this frame, where the object is located. So it will just say the xy, like where is the top xy and the bottom xy coordinates in this. So it's like the pixel, it's like pixel values, but it's not exactly in that. This is more normalized value. These are normalized values, so they don't say the exact pixel values. For example, if it is a pixel value, then it should be in range of, like, if this is a 200 by 200 image. For example, this is 200 by 200 image, then it should be in the range of 0 to 200, the pixel XY value. But in our label, it's it's not in that, it's less than 1 because these values are normalized values. So this is a that is so the train folder will contain all the most of the images. Then there is a test and validation folder. So test and validation is done every epoch. So when you train the model, in every epoch the validation is done. So you have to train the model multiple times. So using this data set, you'll feed this data set and you'll use the train program, and we'll run the program. So the program will take a number of images at once. Like that is called batch size. So batch size, if you declare batch size as 10, then the program will take 10 images and it will convert the 10 images into it will do the same process to the 10 images, like the process that we uh, like similar type of convolution, max pooling, all these different type of packages. So in YOLO V5 it will be different. It uses the different this is a simple CNN architecture, and in YOLO V5's case the steps will be different. So it will take the 10 images and it will do all these operations to that, and then it will take next set of 10 images. So it will go through the whole data set, and then it will create parameter values. The specific, so it has multiple images to get these values. So then it will create weightage values. So this particular specific object means these are the weightage values, and this another object means these are the weightage values. So it will create the weightage values, uh, and it will save the weightage values to a file called a weightage file. So that it could be it could be with the in case of YOLO V5 the extension will be .pt. .pt, some name .pt. It will be saved to that model, and then again it will use these weightage parameter values, and it will use these validation images. So the validation of images will be less number of images. In case of train, there was 300 images. Here in this case, there is only 96 images. So the validation dataset will be much smaller than the train dataset, because the validation dataset is used for uh, validating whether the used for calculating the loss function, how much we are different, how much we are away from the actual output that we need. So that is done in each epoch. Loss function is calculated in each epoch. So this data set will be created in that way, like validation test. When I go to generate and say create a new version, it will save the data into different folders, test, train, and validation. So in this case, we can't create a new project to show the annotation process. So I'll just log in with another account. So here we have already have a project created called vehicle detection. I can so if you want to create a new project, you can just say create new project, and you can select the project type. So object detection or classification, or yeah, instance segmentation. So segmentation is much more useful than object detection, because object detection will be in bounding boxes and segmentation. But the annotation part in segmentation will be very hard. You have to draw the boundary around the object, so we can detect the shape of the object. So it is much more efficient way to detect the objects. So then select a specific type of, then you can just create, name your projects. You can give some name, and you can say what type of object you want to detect. So if you have, so just give some name, and then you can just keep it private or public. So you can just create it as public so other people can access and other people can download and use your dataset. So create a public project so that then you will see a project here. Then afterwards you can just upload the images. So images means in my case I don't have any images right now. So I'll just download some image, some images. So whenever you're creating data set, you should not just use Google images because Google images means it will be you need to use like you can find like real data sets online. You can find open data sets online, like just the images, and then you can use some tool like this to convert that to your specific format. It might not be in the same format. Each architecture has their own specific format. So if you're using PyTorch and YOLO V5, then you have to create a data set in a particular way. Like I've shown you, like valid tests and labels and all that. If you're using some other algorithm like mobile nets that we used yesterday, then you have to create a data set in a different format. So then just add another one more class. So that's so it is better to just use some of the any one of the online data sets. So we have three. Can use these in JPEG images. Okay, we'll just use these two to create two classes, truck and car, and so download and download one. So just drag and drop, or you can just use the upload option to upload the select from folder, select files of folder option. So I've added two files here. So in a real case, even if you're just making a personal project, then you can just, you need at least like 1,000 images to get a better to working model. So then the next save and continue. Then assign images. So assign you can't assign images right now because you need to annotate the images. So to annotate, so there is a one unannotated zero. Okay, that object that we have created is not there. So car and truck. So we have already two classes are there, car and truck. So I can just so to draw the bounding box to annotate, you can just press here annotation and you can see these dotted lines here. So you can just press somewhere on the corner. So you will cover the entire object. Then just draw the bounding box over this. So then just uh, write the object name, the class name, bus. So right now we have created a new class called bus. So then we have two other classes here, two other classes here, car and truck. So you can just create a data set like this. So this is the first process here. Then, so once you created the data set, you can just add one image to the data set. Then it last 70% will go to train folder, 20% will go to valid folder. all the images that you have. Then 10% will go to test folder, add the images. Then you can just say press create a new version. Here you can configure the dataset in your way, like pre-processing. What are the different steps you need in pre-processing? Resize the specific dimension that you need. So it depends on the architecture that you use and the whatever you have mentioned in your training program. And so if this is okay, then continue. Then we can use augmentation. Augmentation means it's a diversifying. It's a process of diversifying the data set. So for example, if you have 100 images in your data set, you want to make the dataset much more diverse. That means we can manipulate the existing dataset and create new images. For example, you can take a existing dataset image and you can just flip the image or flip the particular like bounding box in that image, or you can or blur a specific part or cut out a specific part mosaic. You can add multiple images and you can take multiple images and add them and create a single image from that. You can convert that to grayscale or hue, or you can check the saturation, different type of rotations and cropping. So this will create more. This will generate a much more diverse. So augmentation already exists in YOLO V5 architecture itself. It's an inbuilt thing in YOLO V5 architecture. So that, but we can apply as a user. You can apply this before that. Then you can just press create. So there are four images in that one bus, car, and two trucks. So then you can just three images is out of train, one image is valid, and there is no images in test. If there is, uh, so there should be images in valid and train. Then you can just use the export option to get the dataset. You have two options. Either you can download the entire dataset to your local system if you have a system with which you can train that model. So normally we need a high-end system with a high level GPU to train a model like in a YOLO V5 model. It takes so much memory, so you can't just use a normal system that you have a basic system, basic laptop you have. I can't train the model in my laptop because I only have 4 GB GPU, and my CPU is not. It's only i5, and GPU is not that efficient. It's only like 2 GB or 4 GB, something like that. So I can't train it. If I try to train, after some time the program will get stuck and it will say out of memory. So you need a high-end GPU based processing system to train the model. So it is better to use some kind of online compiler, like so you can use we can use Google Colab for that. Google Colab. So you can use we can use Google Colab to train the model, and we can use this online repository code. You don't have to develop the entire architecture from scratch. You can use an existing uh, repository, free repository. Like this one is the useful one, Ultralytics YOLO V5. So this is the YOLO V5 open source repository. It's a GitHub repository from here where you can. It's a GitHub project. So they have created it as an open source project. You can contribute to it. It's already done, and you can use it. So there are like I can just open the repository. So this is the repository here, and you can just see how many, like you can see the downloads and how many ratings are there. So this is used to by so many people, like even like product-based companies uses this repository. Either they use the whole thing or they use parts of this to implement their own products. So here this repository, in this repository, it provides a it's a Python-based project. So it provides a train.py program to train your model, and then there is a detect.py to detect your objects. Then you can edit this detect.py to create your own application. So you can just you do that. You can just go to Google Colab. So you can just use this notebook here. So I have this notebook. This is all open source, so you can use it freely. So then you can just mention you need to clone the GitHub repository to your Colab. So the Colab means the Colab will provide a system. Here you can see the GPU connected to runtime. It is connected to runtime GPU, uh, T4, and here then you just clone the repository, download the repository, clone the repository to your Google Colab. So you can see it's downloaded the repository here. Then now once you're done with that, you can just go and create the directory, datasets directory. So it's still running. So this will, I can't show you the demo here because it will take time. You don't have the time to do that. So you can just type this yourself, and then afterwards here you can add your own specific data set. So you can just show you select the show download code option and just select the format. So we are using YOLO v5 with the PyTorch. So select YOLO v5 with the PyTorch and just give continue. So we'll show the download code. So this is a download code, and just copy that, then paste it here. So delete this cell and paste it there. So just we have created this vehicle detection. This is our dataset. Then you can just say download the dataset. So the whole thing is executed. So you can just say download the dataset. So here, first it is trying to install the RoboFlow library, but it's already installed. Everything satisfied. It's downloaded the dataset. You can just refresh the file system here. You can find your dataset here. This is the dataset vehicle detection. And we have two folders, train and validation. And then you can use this train.py, you can use the cell to run so here the image, like the same dimension that we gave, these are the different parameters that we need to pass to the program. 650, 640 is the dimension, so the image is 640 by 640 by 640, and batch size. So this is a batch size. That means at a time how many images are used. So 16 images are used. So batch size depends on the kind of system that you have. So if you have a high-end system, then you can increase the batch size. By increasing the batch size, you will reduce the train time. So how much time it is taken to train the model. So then epochs means how many times you should repeat this process of training. So you should increase the number of epochs. You should not run it. It should not be like very low number, like one or two or three, something like that. It should be like 100 or 200 times, because more epochs means the system will be much more accurate. So it's not like in the first epoch it's going to get it's not like the 100th epoch it's going to get the best model. The best model could be in between, or it could be the 100th epoch. So we don't know which one is the best epoch. But the system here, it will select the best epoch and it will name it and will save it to this save it your folder. So if you then This is just the default model, so you need to mention a existing pre-trained model here. You can just run here. So this will run 100 times. This program will run the model, will run it 100 times. So right now it is running. So this is the first epoch, and it's done with the first epoch, second epoch, third epoch. It's going very fast because there is only 4 images. If you have like 5,000 or 10,000 images, then this one single epoch will take minutes, and the whole training process will take hours. So that is one advantage of using, disadvantage of using Colab, because Colab it's a web-based, you know, application. So that means you need to click this is every time. Otherwise, this will get disconnected. So a person need to be there and manually do this. Otherwise, you can just edit the script here. You can edit the script and you can make it look like someone is clicking continuously. So either you can do that, or you can just manually click every minute or something like that. So once it finishes, right now it is going very fast because you only have 4 images. So then you can just check these values here: box loss, uh, GPU memory, object loss, class loss. So these are all different losses that is used for comparing the create, to see how much accurate how much good the parameter values are, how much good the weightage values are. Then there is MAP, so mean prediction average precision at 50%. So this means if you give threshold of 50% confidence, how many object classes are there? Like how many object classes are there? Like if you give a threshold value of 50 to 50 to 95, how many object classes are there? So and that ratio is given here. So within each epoch, it will increase. These loss values will increase. And so these MAP values will increase. So in this case, it is not increasing because we don't have a valid data set. Then it will save the result is saved to runs train exp. So train exp, you can just refresh and you can find that in YOLO v5. So in runs train exp, you can file so many different files. Uh, So these are all like different curves that you can use to decide whether your model is accurate or not. Then you can find the weightage for weights folder where there are two files, best.pt and last.pt. So the last.pt is the last model that was created. Best.pt is the best weightage file that was created. So we will always use best file. So you can just download this weightage file and you can add it to your directory. Colab directory, which I already have here. Colab directory here. Like in my case, I can just add it to this exp. And this is my data set, the data set that I have used. So this is the data set that I have used. I've annotated all these images and created this data set here to detect different objects like cars, trucks, and then the two weightage values are here. So this is the program, the detect.py program. So we'll just see the demo here right now. So this is the detect.py program. So then we have the Firebase programming. So Firebase, what will do it will just uh, once an object is detected, I've given I've, I've given that crop the specific object from that image and save that crop object image as out.jpg to this folder here to mod folder. In mod folder, you can find the image. So this is the last time when I run the program. When I execute the program, this is the last time the object that was the car was that was detected. Then again, it uses this recognize.plate.py program to recognize the number plate or number plate, and then each number plate that recognized will be saved to uh, this CSV file. So like here you can see right now I've just executed this like 1 hour ago. So you can see the date 1/12/23, 14:53, 2:53, and the license plate number, the type of vehicle was sedan, and the license plate number. So I was using a YouTube video, so that's one of the advantages using this directly. You have multiple options to give input. Either you can give your laptop or your system webcam, or you can give a input image, single input image, or you can give a video, or you can give a screenshot path to a directory with images, or you can just give a YouTube link. You can just give a YouTube link. So I'm just using a YouTube link here to run the program. So this is yesterday, same as yesterday. Python command and the file name, then the weightage value. So uh, I'm using best.pt weightage file to detect objects, and then confidence threshold value I've given it as 80. So we don't need to give like so much. Right? I'll just give 40. Yeah, there will be so many wrong detections, but still we can see a lot of object bounding boxes. If you give 80, the number of bounding boxes will be very less and will take so much time. So then I'm just using this video here. So I can just show you the video. What is the video? What does the video contain? So just a traffic store video, and it has so I chose this video because it has different type of vehicles, and it has cars, and the number plates are visible. So in so many videos, the number plates are not very visible. So in this case, number plates are visible, so you can see some results. So that's why I chose this video. So this is a video here, and I just given. And then we can just run this enter. Will run the program. So the CSV file is open. That's why it says permission denied. So we should close the CSV file before running. So initially it will take some time to start, then it will be faster, but it won't be as fast as yesterday's mobile nets. It is it's taking so much time to process a single frame. So right now it's detecting the car. It detected the car, and it detected the car and it recognized the license plate. You can see the license plate here. That was the car that was detected. Then we can just see in our mode directory the output file that was saved. So the car. Then next thing is the Firebase. I've created this Firebase account. You can create it for free, and you can create it. So in that you need to in build options. You can create a storage. You can create a storage, and you can just create a storage, and you can go to project settings, service accounts, and you can just go to the option manage service, and here you can just download your the JSON file, which will give you the permission. So here you can just manage keys, and then it will show. So right now, so add a key and create a new key. So it will show this create a key like this. Then you can just here there will be option here to download the key. So then you can just download the key. If you download the key, it will be so let's just download the key. Key will be like something, yeah, something like this here. So it will just something like this IoT test. So this key here, I've mentioned that in the program, Firebase would be with a JSON file. So this is the permission file. So that then it will upload the image to the Firebase. Then it will upload the image to the storage. So you can just go to storage. You just go to storage, and this is the same image that was uploaded. So it's taking some time, but it's the same image. You can see it's even showing the whole name or the whole path is given as the name of the image outbound JPJ. So it will say whatever object that detected, it will upload the image. So this could be like an application in which you can just you can have a traffic system where this could detect uh, different vehicles, and if there is any violation, like for example a violation example, I can show you one example. I can show you that. Just play a video, previous video. So this is just a small project we created. So here is the same use the same similar kind of use the same YOLO Wi-Fi architecture, and this is small model here, and we have a crosswalk here, a zebra crossing, and then there is a red light detector, and there is a and the car is being detected here. So car is being detected here. Whenever there is red light, if the car crosses this zebra line, right now the car is just in front of the zebra crossing. But when if the car while the red light is on, if the car crosses the zebra line, then the car's license plate will be detected. So you can use another camera to detect the license plate. License plate will be detected, and that license plate. So then the value will be saved in license plate will be detected, and that will be saved in the CSV file I was showing you. So here this is here I have three classes here in this specific project. Three classes are there: car, crosswalk, and red light. So the confidence values are very low because these are like small toy cars. If you have a real time video, then you'll get a much more better value. So I can show you that here. Car detection, you can see is detecting the cars from a actual video. So you can see the confidence values are very high because this is a real car. So toy cars will with the toy car and a toy setup, the accuracy will be, the confidence value will be less. This is more because we have given actual images to train the model. So this is another way in which you can integrate Internet of Things and machine learning. So here the it is detecting every license, it is detecting all the license plate available in that in the image. So whenever there is an object detected, it will just take the license plate and then it will create a CSV file, and the whole everything could be the CSV file and the image, everything could be whenever there is a violation. Instead of uploading every image, yeah, if there is a violation, we can just make this to upload only at that time. So the traffic police, they can just go on a like daily basis, they can go and check their cloud storage, and they can see how many vehicles are there, how many and they can download the CSV file, and they can see the timing. Based on that, they can analyze that and they can provide take actions. So this is one of the examples of integrating IoT, Internet of Things, with machine learning. So thank you guys. That's all the time we have. So thank you for the Thank you for listening. I hope this was helpful for you. So this you can just use as a start, and you can try your own. You try to create your